So I'm Udit, and thanks for the kind introduction. So I'll be talking about evolving risk profiles and resilience of built natural systems, and in this talk I'll try to cover various things that we have been trying to do at our lab and fortunately I've been part of. So in the morning Arup talked about this figure from World Economic Forum that classifies many of the climate and weather related hazards as high risk and high likelihood events. But when we talk about climate change and water related stresses, what do they mean in the context of weather sciences? We are looking towards higher evapotranspiration, higher evaporation, more holding capacity for water in the atmosphere, which results in more intense and severe storms. That means faster runoff, and which eventually translates to less groundwater recharge. So we end up with the scenario that where we are susceptible to floodings as well as water logging, plus scenarios like drought, because our groundwater recharging is not happening at the appropriate rate. So if we put this in the context of weather extremes for infrastructures, and this is the figure that I borrowed from IPCC, which says that like when we talk about changes in climate and indices of extremes, there could be shifts in mean, changes in variances, and changes in both mean and variances. So when we translate these changes in statistical attributes of these extremes and what do they mean for infrastructure design, that means some of the infrastructure relevance indices which have been used for past centuries to design infrastructures of today, for example return levels, would not be the same. For example, the 100-year return level that we anticipate today could be a different return level, because it's just a way to define it statistically, and 100-year return levels may not be a return level which corresponds to same level in near future, as a result of which the design standards to which we have designed a particular infrastructure would not be able to long stand those events that it is facing. And hence we look at identification of changes in infrastructure relevant indices, where return level is one of them, and if these changes are happening, how these changes are clustered. Because when we talk about design standards, we look at system level analysis, and we really want to see that where these hotspots are located, so that we can classify them as high risk zones, medium risk zones, and low risk zones, and so on. So we started doing this exercise with Professor Mukherjee here, where we started looking at how 100-year precipitation extremes are changing for India, and we got this data for a long period from IMD. And what does these changes in return level means if we look them if we try to put them in perspective of zones, and if we have these zones, how do they cluster in space and time? So this simple exercise gave us a few interesting results, that if we look at changes, these changes are strongly aligned along the elevation and topographical properties across the nation. So what? We know that these extremes are changing, these indices are no longer true for our design standards, but what should be the next steps? We know that risk has changed, but how we can translate this changes in risk to more well-informed design practices and resilient practices? Because with changes in climate and changes in statistics of extreme events, the failures are no longer isolated to one single system. And this is one of the classic examples that we talk about, that in 2012 there were delayed monsoons and series of heat waves in north part of India. These two combinations in combination, these two events in combination with peak agricultural season, where there was a huge demand for water to sow rice, resulted in surge in agricultural water demand. Combination of these three factors made farmers pump more and more water from the ground. Air conditioners were running at full capacity in the urban cities, and these three events then resulted in localized failure in a few parts in power grid near Kanpur and Jhansi. Within a few hours, that localized failure resulted in world's largest power failure in terms of number of people impacted, because the load distribution took place, and within an hour around 50% of states were engulfed in the power blackout. It didn't stop there. That power blackout then propagated to transportation networks, and transportation networks being lifeline of the nation crippled financial and economic sectors and so on. So we started questioning that is there a better way where we can harness all the data sets that we have at our disposal, which includes remote sensing data sets, observations from gauges, observations from radars, and put them into a meaningful metric that can help us characterize risk and resilience better. So we started looking at outputs from Earth observation systems, plus combining them with multimodal outputs coming from CIMIP, which is Climate Data Repository, and running them through physics-based hydrological models to get better estimates of extremes, changes in return levels, and what these changes in return levels actually mean for revised flooding scenarios for various cities. So far, the community is divided into two approaches, where one focus of one community is strictly on physics-based models, and another part is on data-based models. Physics-based models includes the umbrella of models that we talk in hydrology, which are hydrological models which try to model these physical processes in forms of differential equation. We solve these differential equation, parameterize them, and get the solution. On the other hand, data-driven models, they are focused more on improving predictive or forecasting skills, but they often ignore that what is the feasibility of underlying process which may result in spurious insights. What we propose here is hybrid physics data model, that can we combine best of the physics based processes with best of data based processes, which include our predictive ability or predictive skills without losing the insights that we have about the system. So we took this small basin in Massachusetts, which is Charles River Basin, and started to look, can we model the various processes, the hydrological processes in this basin using state-of-the-art physics-based model. We calibrated these models, and for training period and for testing period we got very nice results, which and when we looked at one of the metric that talks about NS efficiency, everything was good, until we noticed that event where there is a larger deviation between observations and simulated stream flow. When we zoomed into certain events, we realized that while these models, they are able to capture details to some extent, whenever localized or specific processes happen in these basins, the results are thrown away, and that is the period where most of the Charles River is frozen. When Charles River is frozen, certain parts slow down the stream flow, as a result of which even the parameter scheme that we have calibrated in training period would not generalize to those specifics where those deviations in the physical system are taking place. To encounter this problem, we started looking at how we can combine what we know from physics, because that model was working well for most of the part, with data-driven models which are good in calibration, which can capture these anomalies or detect these anomalies in training and testing period, and try to combine it with physics-based processes to improve the overall understanding of process as well as improving the predictability. So this goes like a typical neural network, where you have a feed forward process, then you have a back propagation process where you try to learn from errors, adjust your weights in both physics based models and data science based models, and try to improve the overall skill of your model. We applied this scheme to Susquehanna River Basin, which is a larger river basin, and it gives us number of points and a lot of data sets to validate our model. What we started looking at, we tried to formulate an objective function where we included not only the regularization terms that comes from typical data science, where we try to impose Occam's razor type of simplicity, but also include physical constraints, and if model is producing some values which are against the physical feasibility, we penalize our model. For example, our predictive modeling is working great. However, we realize that it is giving us value of stream flows on dry days, that is no precipitation is taking place, but just to improve the overall predictive skill, it is giving us value of stream flow which are abnormally high. So we penalize those variables or coefficients which are coming out of the blue, that is, they have no physical realism, but they are still present, improving overall predictability. So combination of this regularization that we learn from data sciences plus regularization from physical constraints has started showing some initial results which are giving us better reproducibility of statistics of stream flow to begin with, and with improved understanding of the processes. Now we have this improved predictability, improved understanding of the processes. How do we translate this impact to risk and resilience? Because we have been talking a lot about networked systems which are dependent and interrelated. So when we understand what is happening from the hazard side, what is the solution? So we started, we looked at that how we can develop some of the methods where we can translate some of the understanding that we get from impact side to inform the resilience side, that is, once systems are down, how we can recover, where we look at single networks, interdependent networks, multiplex of networks, and so on. And we look at systems like real world systems like Indian Railways, US National Airspace, that if events like power failure in the middle, tsunami, events like tsunami that happened back in 2002, or even simulated cyber physical attacks have to happen on these systems and bring these systems down to knees, how we can intervene into these systems and inform our recovery strategies that can result in faster and efficient restoration. For example, this is an example of New York MTA where system was down after a flooding because of Hurricane Sandy, which resulted in complete deadlock in the city because trains were not moving, people were stranded, and we modeled the New York MTA's recovery, that how they recovered in real time after that flooding event and what our proposed algorithm is suggesting. So what we found, on the left we have the proposed algorithm that talks about how we should prioritize our resource allocation after events like flooding, and how New York MTA actually recovered, and we got this data from the real ticketing data, that how they started generating the revenue once system was down. So what we realized, that if we have better assessment of hazard, that where hazard has actually struck or is likely to struck, if we have understanding that where we should pinpoint the priority or prioritize the resource allocation, we could save millions of dollars just in terms of how faster we are restoring the operations. So in this case, we could have saved additional of $56 million just by expediting recovery, because now more people would be able to use the train, and hence business would come back in real time, and hence more revenue would be generated, which can be used to speed up these operations. So this brings back me to the initial picture, that where we are working on is that how we can improve, assess the hazards, both which include natural and climate related hazards, and once we have better estimates of these hazards, how we can translate this understanding to risk and resilience, which could help us speed up recovery and design a better world. So this is of course a brief discussion about various things that we have been working on. For more details, here are the list of citations that you can refer to. Thank you.
Thanks, Udit. Any questions? I have one question, if I may. So, when we were pitching the data model,
Yes.
in the Susquehanna data lesson, and you said that the data model overestimated the stream flow on guidance, right?
Yes.
Now, did you take into account of the groundwater risk flow, or secondary back storage water discharging the system?
So in general, we account for like whatever we are getting from the parameterization scheme that we have designed. So now talking specifically that what kind of physical constraints we were looking at. So for example, there was a dry spell of 5 days or 6 days, and one of the runoff generation processes is subsurface flow. If we see that there is a parameter spike in the contribution of subsurface flow, then we penalize that, since it is not always feasible to look at the data, the kind of flows that you were talking about, because we really do not have direct observables for that. So we generalize this penalty term to penalize those kind of flows. But as more and more data is available, we can modify that how we are penalizing our physical constraints and include those parameters. But right now we just go with like a feed forward process, as I mentioned, look at whether that anomaly is happening and the time period, or for example, if we drop of water on top of the hill, we get that time of flow, concentration time from physics based model. If we observe any anomaly taking outside that time of concentration, we treat that as anomaly and then penalize our parameter and physical space.
Just a quick suggestion.
Yes.
The US Geological Survey do have gauges.
Yes.
Yeah. And also at least 3 gauges.
Yeah.
And they do have like 50 years of almost hourly scale data that you can get out of it.
Yeah.
And possibly you can backtrack your model, to separate out the gauge flow from the the sufficient flow, and feed in as a forward simulation the model.
And that's a great idea, and that's exactly what we are trying to do, right? That include more and more granular information that is available at station gauges, and look at like how it is, how much error and how much residuals we are getting at each gauge location. That could help us tune these variables in a much better way. Yeah.
I understand that you would have used digital elevation model.
Yes.
What is the resolution of hosting that you use?
So for this particular thing, we use SRTM, which is a 30-meter resolution.
Do you use higher resolution because US you still get better quality data? And my question is, in case you did, do you also do comparisons as to when you're using high resolution data, how much does your result vary? Because finally, it gives us some kind of benchmark to understand India when data is not available. So when you use open source, that what would be say variations that you can expect, what band?
So again, this is an excellent idea, especially so this is the case study for Charles River Wellesley, and we did this work like 1.5 years back, but now we realize that Mass GIS has produced data at ultra high resolution, and now we have procured like through their open servers those high resolution data sets, and we would try to use that to model high resolution DEM as one of the inputs of our physics based hydrological model, and it would be interesting to see that how they compare, but we have not done yet, but that would be an excellent step. Yes.
Understanding here
Yeah.
as to what is the variation that takes place.
Yes, exactly.
What he's suggesting is to do a sensitivity analysis,
Yeah.
resolution size.
Yeah.
This is an excellent idea. I would suggest we.
Yes. Yeah.
This is something which is not, the data is not available. So if we know that how much variation does data get, it may be possible that it is not too significant. So then it gives us a confidence that whatever we are developing here has some, if it is not, then we'll have to make some interventions for specific areas where human aspects are concerned. We'll have to take it up with yes. That can make sense.
So you can take one last question.
Just actually more comment. Just a quick reaction on this is that